Okay, so we are now going to cover section 2.7. That is the main thing that we are going to cover today. The homework problems for these sections are, let me use the red pen. Section 2.7 homework problems are, let's see, 2, 3, 4, 10, and 11. So I ask you to hand in number 2, number 10, and number 11. Okay, those are going to be due on April, I think April, should be April 8th. So give you plenty of time. And then so Wednesday, I'm going to post this on the assignment, under assignment as well. So I want you to read this section carefully. Then I will just go over the textbook material now. Then during lecture time on Monday, which from 6 to 8:40, I'm going to go over it live in more detail. So what is a Fourier transform? Fourier transform is similar to the Laplace transform, is another integral operator that we use to solve a partial differential equation. The definition of the Fourier transform is given by this. So let's think about it for pause and think about it for a moment. The function that we define on u is now a function that actually we now x is the variable, is a spatial variable. It's actually from negative infinity to positive infinity. It could be real value function. It could be a complex value function. Then we integrate against x, and then we modify this term here. So let's compare this with the Laplace transform. Lu, we have s is the phase variable, and it's from 0 to infinity u t e negative st dt. Okay. The fundamental difference here is that in this term, we have, this is a complex, it's a complex number. Remember, EICX is cosine CX plus I sine CX. So if x and c are both real variables. So this is what you have here, the Fourier transform. After you do the Fourier transform, the function could still define from negative infinity to positive infinity, but it is necessarily a complex value function. So that is the one of the main difference. Now for this, not every function can define. You can have the Fourier transform is defined. For example, if u is c, if you want to define the Fourier transform of a constant c, then you would have this integral, and this actually is undefined. This is an improper integral. And then you can see that this improper integral is not convergent. So this is not defined. So the point is that Fourier transform would not define on any function. So it is a very ingenious idea by a French mathematician called Schwartz, and then he defined a class of function where you can define a Fourier transform, and this class of function is usually referred as the Schwartz function. The Schwartz function are what we call as rapidly decay functions. So rapidly decreasing function or decay function. And it means that the function and any of its derivative would go to zero faster than any power function goes to zero faster than any power function as x goes to infinity. Now, then the good thing is that under this, for this class of function, the Fourier transform actually would become the a linear transform from what is happening for my pencil? From this Schwartz class to Schwartz class, and then we can prove that this map actually is 1-to-1 and onto is a bijection, is a linear bijection. But we are not going to do that in this class. So the idea of Fourier transform is actually similar to the idea of Laplace transform. What it means is that when you have the derivatives of the function, then you calculate, to compute the Fourier transform, then it actually we have this very simple formula for the derivative of the Fourier transform. It's just modifying. It's kind of similar to the Laplace transform. It's just modifying this term. Now, we don't have boundary term here because in our assumption, we assume that this u is a rapidly decreasing function. Now, let's see how this formula comes about. Let's say we want to calculate the Fourier transform of the first derivative of the function. So by definition, it is from negative infinity to positive infinity e I cx and then ux dx u prime. So we use this term. We use integration by part. So this I write it as here. So this is ei cx dux, and then after integration by part, then we have this is I c, and then this is integral of this x e I cx dx. So that is now we did not have boundary term because u at negative infinity and u at positive infinity is 0. Okay, so that is why we don't have it. So therefore, that is how we arrive at this formula. Actually, in the definition, we should have I should have a negative term here when you do integration by parts. So therefore, it's EIC. This is the Fourier transform of u. So usually write as u hat of c. C is the phase variable again. So this is for the nth kth order derivative. You can prove this formula similarly. Now when we use the Laplace transform, we apply the transform, the integration with respect to the time variable. But here, the integration is with respect to the space variable x. So that is one of the difference. And then when we solve a partial differential equation, here in the Laplace transform case, we ignore the space variable, but here we ignore the time variable. So that is the point. Now, so the idea is that you have a differential equation, and then you use a Fourier transform to transform it into an algebraic equation, and then you solve this. In the case of PDE, this is an ordinary differential equation, and then you need to solve this, find a solution. After you solve this equation on the right hand side, you use the inverse Fourier transform to find the solution. So the definition of the Fourier inverse transform is this formula. So you notice that, I mean, in different textbook, it actually, the definition actually is different. Some use positive here and use negative here, but in this case, we will follow the textbook. And notice that here there's a factor 1 over 2 pi, but here there is no factor 1 over 2 pi here. So that is the difference. All right. Now, let's look at these are the examples. I want you to read over it carefully, and then we will talk about this during the class time. So you look at example 2.13. That is, you want to compute this the Fourier transform of the Gaussian function. It turns out that you look at the computation. I mean, you can do the computation as by computing the square and then as before, and then you will be able to find the solution. But here they do the computation using by reduce it to a differential equation. They differentiate this, and then you take the differentiation inside the integral. And then therefore you have this, and this becomes this, and these are the same, and then you convert this to an ODE, and you solve this ODE, and the solution is this. And then you look at the initial condition, U0, and then that equals to the constant, and therefore you have this formula. So we will go over the details. We will go over the details of this during the class time. So I want you to first read these examples by yourself. And then you can also do this integration by just think of this integrand as x squared plus I cx, and then you complete the square of this. And then you can do it, change of variable, and then you can also find the solution. So what is the remarkable thing, which actually is one of the things why the Gaussian function is so useful, is that the Fourier transform of a Gaussian function has a form that actually is also, the right-hand side is also a Gaussian function, but with different constants. So that is what is an important property for the Gaussian function. Now, here in this next example, we have a function u, which is called a square pos function. So the function, if you want to draw the graph of the function looks like this. 1, -1, and this positive greater than 1 is 0, and this is positive 1, and this is less than -1 is 0. So this is a square pos function, and you just calculate the Fourier transform. So the Fourier transform again is, now the function is only non-zero from -1 to 1, so therefore in this case is 1, and then e I c times x d x, and then if you integrate this, and then you will see that this is exactly what we have here. So I want you to do the detail, and next time I would during the class I will show you the details. Now, one of the properties that we have for the Laplace transform is also is true for the Fourier transform. That is the convolution. Notice that in the convolution here, the integral here is from negative infinity to positive infinity. So remember, in the Laplace transform case, it is uv t here is the integral is from 0 to t, and u t minus tau and v tau. Now the difference, the reason for the difference is that this uv, we can regard it as a function that is defined when t is greater than 0 as u, but then we extend this function to 0 when t is less than 0. So that in this term, when tau is less than t, tau is greater than t, here this term would be 0. That is why the integral is from 0 to t, and then when tau is cannot be less than 0, because this term, otherwise this term would be 0. So that is why. But these two definitions actually of convolution actually are consistent to each other. It's just that for the Laplace transform case, the function is defined only when t is greater than 0. But in this case, u is supposed to define from negative infinity to positive infinity. So that is a difference. Now, we also have a convolution theorem as what we have in the Laplace transform case. That is that under Fourier transform, the Fourier transform of the convolution is the product of the Fourier transform of each individual function, and likewise you have the inverse of the product is in the phase variable is the convolution, in this case in the spatial variable. And this example, the next example, 2.16, tell you about how to use the Fourier transform to solve a differential equation. You have this is an ODE, and then in order to solve it, you apply the Fourier the Fourier transform. You apply f to both sides of the equation, and then this is the Fourier transform of f, and these are the Fourier transform of the left hand side. And then this is now an algebraic equation, and it is negative, so it's negative or c squared plus 1 u hat f hat and u hat are the Fourier transform of u f and u. So then this is an algebraic equation. You just solve for u hat, and then you get this expression. Now this is a product on the Fourier transform side. Therefore, on the original function side, it should be a convolution. So that we know that the Fourier transform, you are going to do an exercise number 2, and then you know that the Fourier transform of or the inverse Fourier transform of 1 over 1 plus c squared is this function. So therefore, the solution is then the convolution of this, and then that is the way to write a convolution. Then that is how we have this example. Okay, sorry. So now you can also use Fourier transform to solve PDEs. That is example 2.17. So here you have a heat equation. This is a heat equation on the real line. This should be x in R. And with this initial condition. So here then the first thing you need to do is you apply Fourier transform to both sides of this equation. Let's write the equation as ut equals to k u x x, and then we apply Fourier transform to both sides. So Fourier transform is also a linear transform, so the constant, you can take it out. All right, now you need to be careful. Remember that in this case, the transform is applied with respect to the spatial variable. So therefore, this thing here, we did not do anything with the time variable. So this becomes the Fourier transform of u, but the derivative with respect to t. But on the other hand, on the right hand side, the Fourier transform of the second derivative of x is, as we said, we go back to this formula, this formula that we have over here, this formula here. Then we have, we know that this is, this thing is negative I c square u hat. So that is why we end up having this equation here. Now then this is become an ODE, so then you can solve this this ODE easily, and that is the solution is this. Now then we need to determine this c, this constant c, from the initial conditions. So that means that you apply the Fourier transform to both to this equation, and then you find out that this c actually is the Fourier transform of f, and that is why we have this. Now then we need to know that this is from the example 2.13. This example, we know that the Fourier transform of the Gauss function is another Gauss function with this, using this formula here. Then we know that the Fourier transform of this factor here is the inverse Fourier transform of this is this function. Now then the solution is then written as the convolution. So it's the convolution of the inverse Fourier transform of this, that is this. So this actually is what gives us this formula here. Okay, so now the other example here I want you to read over is example 2.18. Now here you get a Laplace equation, and with this boundary condition. Now we actually have two spatial variables, x and y. So we just fix one spatial variable as a parameter, and then we apply the Fourier transform with one of the variable. In this case, we would the Fourier transform would be taking with respect to x. So when we take the Fourier transform with respect to in this equation, so we have this. Now you can also take the Fourier transform with respect to y. But in this problem, you should take it with respect to x. So we get this. Now remember, the Fourier transform is taken with respect to x, so therefore this term becomes negative I cx no, there's no x, just okay. So this negative I c square u hat plus u hat y. So this just write down here. So then this becomes this equation here. And this is an ODE now for u hat. This is an ODE, the derivative only with respect to y. So then you can solve this equation. Then you need to determine this a function a and b. So because we assume that the function remains bounded as y goes to infinity, so therefore we drop this term here. So therefore we have only actually is let me go back. We will drop these terms for the better way to say it is, let me not say that we drop this term. The better way to say it is that we can when c is positive, then we if this is going to be bounded, then we should drop this term. But when c is negative, we should drop this term here. So that therefore, at the end, this is our the Fourier transform of u hat of u, and then so because this is and then by the boundary applying to the boundary condition, then we get that this c is actually the Fourier transform of this function f. Now therefore the solution the solution is then the inverse Fourier transform of this function, which is, this is a product, so it would be a convolution. So the inverse of Fourier transform of f hat is the original function f, and the inverse function of this term is this term, and this is actually the formula for this. And if you read other textbook, this actually is usually referred as the Poisson kernel on the upper hat plane. Okay, so this is a guideline for you to read over section 2.7. Let me remind you that I asked you to do homework number 2 and number 3. You don't need to hand in number 3, and number 4 and number 10. You need to hand in number 10. And I also want you to give it a try to hand in number 11. And I'm going to talk about this, some of these problems during the live lectures on Monday. Okay, so I will see you Monday in the class, during the class time on Canvas.